Hi, good morning. I'm Matt Traum. Just introduced myself before. So I'm a senior lecturer and associate instructional professor in mechanical and aero at UF. My kind of collaborators, co-authors on this work are Odette Ribas and Jimmy Yan, who, well, Odette's a Santa Fe student, and then Jimmy, probably everybody knows Jimmy. He's in the Career Center, but he also has, well, several other hats, but one of them is he's the president of the Santa Fe Soaring Saints, which is a National Association of Rocketry section in town here. So lots of rocketry related stuff that Jimmy and I work on together. So I'm going to talk to you guys today about a 3D printed altimeter payload coupler to extract flight data from Alpha 3 model rockets, which is kind of a mouthful. But now, can I change slides is the next question. Yes, I can. Okay. So my sort of brag slide, program sponsors and acknowledgements, but then also to sort of give you a sense of like what we did this summer. So we have two kind of complementary summer programs, and that blue dotted line is meant to kind of separate the two programs from each other in terms of like who sits where. So STEM Tank is a program that's basically run by the TRIO office out of Santa Fe College, but we also cover Florida Gateway and College of Central Florida, sort of catchment areas for students. And that whole program is sponsored by the Department of Education. And then here's the lab that I'm affiliated with, the Merge Lab, and of course we're in the College of Engineering at UF. And then we have a second high school STEM summer program, which is called Incubator, and that one is sponsored by Children's Trust of Alachua County, Autodesk, and the Les Paul Foundation, and it's run through CPET, the Center for Collegiate Education and Training. So we basically run these two-week high school summer STEM camps, and we try to use the same curriculum in both camps. And when we ran this thing previous summer, just by like sheer accident, one of the student groups that showed up was the rocketry group at UF. And the students who were in the program last year said, "Oh, we want to do rockets." So okay. So we figured out how to basically run a 2-week long rocket curriculum in the context of these two camps. So that sort of is the big picture background of how we involved high school students and what it was that we were trying to do is get high school students excited about STEM. So here's the big picture of kind of what I'm going to talk about, and then what it was that I did. So we recognize that rocketry is an inexpensive educational STEM activity. Estes, which is a model rocket company, produces something called an Alpha 3, which comes in so-called educator bulk packs. So they're really inexpensive, but they do everything that normal model rockets do. It works out that you can buy them for about $6 or $7 a piece. So it's affordable even at the high school level. We realized that, it's kind of cool to shoot up rockets and watch them come down, but it's even more cool to put an altimeter on them and be able to collect data like velocity, acceleration, altitude as a function of time, because then you can take those data and use them in discussions that are relevant to math and physics and engineering courses. There used to be a company called Jolly Logic that made an amazing altimeter that would fit inside these tiny rockets. The company still exists, but they don't make the altimeters anymore. And so we had to find another altimeter that would actually fit into these tiny rockets. And it turns out there's a company called Featherweight that makes an altimeter called the Raven 4. However, there's no such thing, at least there wasn't before this summer, as an Alpha 3 Raven 4 altimeter payload coupler. So we had to design one and build it and then propagate it and use it in the class. So we have high school students in these two STEM summer camps that use these couplers. And because we're doing sort of pedagogical research to try to figure out the effectiveness of these programs, we gave the students a pre-post self-efficacy survey. And as you'll see, I'll show you the results. We did end up getting some positive gains in what we call the triad of positive STEM participant responses. So all of this ended up working well in that the students demonstrated that they were excited about what we were doing and had self-efficacy growth even over a period of time of only 2 weeks in the camps. So here's an Alpha 3 rocket. Like I said, they're available on Amazon in educator bulk packs. You could buy 12 of them for $80, so it works out to somewhere between $6 and $7 a piece. The skill level here is 0, so they are meant to be built by students that have no previous model rocketry experience. And the key thing, especially if you're trying to do this in the context of like a camp or a class, is that the assembly time is incredibly short. So it's an hour or less. It says painting and glue drying not included, but you can actually have the students glue these things, put them together, sit them up and let them dry. And then, as I'll show you in a second, you can actually launch them on the same day. So you can do programs in really short periods of time with these rockets. Here's the Raven 4 altimeter. This comes again from a company called Featherweight. You can see the top view and the bottom view relative to a dime, so they're super small. And they've basically got built-in both accelerometers and barometric altimeters. And so I'll show you guys in a second that the data trace, you can get acceleration and altitude, and then there's a software that will internally integrate the acceleration to give you velocity and position as a function of time. So we had to figure out how to get this to fit into that. So here's how we did it. We added just a 3D printed payload bay, and we took advantage of the fact that the nose cones for the Alpha 3s are basically hollow. That's not true for a lot of model rockets, but it happens to be true for the Alpha 3. So we stuck the altimeter into the nose cone, it just barely fits, and then the altimeter needs a battery, and so the battery ended up taking up most of the volume of the payload compartment. We snap everything together and it looks like a rocket. So here's kind of a close-up view of the 3D printed coupler showing how the battery fits in the nose cone. And then these altimeters, when you engage the battery, they let you know that they're like ready to take data because they have this red light that flashes. And so this was a worry for us. How are we going to know that the altimeter is ready to take data? Well, the red light actually flashes right through the nose cone. So you can see it flashing on and off. So that was kind of a happy accident, but it works out well. So these are very good for taking altimeter data. This is the engineer in me. My students always say, well, gosh, these things that you guys create in the design lab are so wonderful and perfect, and I could never be as good a designer as you are. And well, gosh, look, I had to go through about a dozen iterations before I got to something that actually worked. And so this just shows sort of the progression of the design from where we started, which was basically a box that held the battery all the way through to the final version of it. Along the way, as we were doing the design, there was a couple of attributes that we sort of discovered that we needed. So I mentioned that the altimeters have a built-in barometric altimeter pressure sensor, and we initially didn't have any way for the barometer to read the atmospheric pressure. So we had to design holes in so that we could get to the atmospheric pressure. Here's where it couples to the body tube. If you're familiar with rocketry, there's something called a shock cord, which is what basically holds the parachute onto the rocket. So we integrated a shock cord mount into the bottom. The top here has the nose cone coupling. And then there's I call it a battery insertion bevel. So maybe if I go back 1-2 slides, the battery slips in, but without that bevel, it's really hard to get it in there and to get it to seat. So we added that feature to make it really easy to put the battery in out in the field. So this, it's a simple design, but it does kind of a lot of cool things integrated into one piece. So here we have it on the 3D printer. The material we printed it out of was PETG. You can also do it with PLA, but we don't like to use PLA outside because over time it gets wet and it degrades. So PETG is a little bit more robust for outside applications. We used about 8.6 grams of filament. You can print these things in about an hour and a half. The filament cost is 31 cents. And the really important thing, at least for us, is that no support material was needed. So all of the undercuts and everything are all 45 degrees or greater, so that you can literally pull this thing right off of the print bed and stick it on the rocket, and you don't have to take any support material off. So it's not super time consuming for the fabricator to make one. So here we've got students, both our STEM tank students and our incubator students, building their Alpha 3 rockets. If you recognize this guy here, that's Jimmy Yan, who again is the NAR president for the local chapter, and then also affiliated with Santa Fe through our Career Center. So here they are having finished built their rockets. And then here we are out in the field preparing for launch. And I made sure to sort of to accentuate same day, right? So they built in the morning and they launched in the afternoon of the same day. So this can all be done in the context of a one-day event. 3, 2, 1, launch. So there's just one example of one of these rockets going up. I have a video, which maybe if I have time, I'll show at the end of a rocket just sort of going up and coming down so you can see what it looks like. This is a little bit of an eye chart, and I apologize for that, but this is the way that the data comes out of the Raven 4 altimeter, and it's really difficult to process it in a way that is any better than this, at least in terms of visualization. But you can see there's 4 data traces here. So we have time in seconds on the x-axis, and then we have axial acceleration in red, let's see, altitude in black, barometric altitude in blue, and then a velocity trace in purple. And the thing to me that's really cool about this is you could see it sort of the initial time here when we fire off the rocket, there's this huge kind of burst in acceleration, and that burst in acceleration corresponds to the rocket engine firing. So there's this really high, steep initial acceleration, and then it kind of 2 minutes, oh no. And then it sort of trails off, and then you get no acceleration at all, at least from the rocket motor. And then there's a corresponding rise in the velocity and a corresponding increase in the position. And then as the velocity falls off and goes to 0, you can see you reach sort of the apogee where you're no longer gaining altitude. So you can use traces like this either in a physics class or a math class to talk about the relationships between acceleration, velocity, and position, maybe talk about derivatives, talk about integrals. And then you can also compare the acceleration data from the accelerometer, which is the black trace. Let me try again. The altitude data, which is the black trace, to the barometric altitude data, which is the blue trace. So you can see that sort of the trends are the same, things are going in the same direction, but the barometer is getting a lot of noise because the rocket is getting sort of buffeted around, especially here when the parachute deploys and the rocket makes its way down. There's sort of all of this buffeting in the barometer signal. So anyway, this comes out both as a trace like this, but then also as streams of data that you can import into like an Excel spreadsheet to do data processing on. Okay, so in terms of kind of the pedagogical benefit of this, we have developed something we call the triad of positive STEM participant responses. So we're interested in measuring kind of a pre-post student self-efficacy study that has 3 key metrics. So one is efficacy. Am I good at STEM? The second one is affinity, which is I like STEM. And the third one is grit, which is the ability to overcome STEM challenges. And for a STEM program, we really want to be sort of at the center of that Venn diagram where we're hitting all 3 of those simultaneously. It's very hard to do in a 2-week summer camp. But if we can get even one of these to tick up in a statistically significant way after 2 weeks, that's a win. So this is the new general self-efficacy scale. We ask students these 8 questions on a pre-post level, or a pre-post timeline, so before the camp and then after the camp. And then each one of these questions... I don't know what's wrong. Whoops. Uh-oh. Each one of these questions is tied to one of those affinity metrics, right? So we've got grit, affinity, efficacy, and so forth. And then when we take the data, so this is actual data from those surveys, pre-post data. I didn't label it correctly, but the STEM tank data is on the top, and then the incubator data is on the bottom. These are just meant to be heat maps that show the pre-post responses of each individual student compared to each of those questions. And so red is a situation where a student gave a higher pre-score than post-score. Yellow is neutral, so they give the same score before and after, and then green is an increase in the score from before the camp to after the camp. And so what we're looking for is sort of... Pathetic. Yeah. What we're looking for is like collections of green along columns. So collections of green along these columns indicate that there's been some sort of improvement in student self-efficacy over the period of the camp. So we ran a Wilcoxon-Stein rank test, which is a statistical test to see whether there was statistical improvement across these categories. And we found that for both camps, students had an increase in their ability to overcome challenges, which is the grit metric. And then for Incubator, they also indicated that they could accomplish hard tasks, which is grit, and they could also do tasks well, which is efficacy. And so we essentially designed and 3D printed an alpha 3 altimeter payload coupler. We gave students this pre-post self-efficacy survey in the context of two-week STEM summer camps, and demonstrated that at least 2 of those 3 triad positive STEM participant response metrics improved over this very short period of time. And now we've got this 3D printable coupler that's available basically for anyone who wants to use it. And so I've got my email address on there, although it's obscured by the
live transcript.
There you go, live transcript a little bit, but yeah, there it is. And that's it. So thanks for your attention, and sorry I went over.
Thank you very much. Brandon, were there any questions in the chat?
There's 2 up there, and there's nothing popping up over here on mine, so.
Oh, because it's Brian's,
Oh, that probably popped up before you logged in on that computer.
Could you remind me efficacy with that I like or good?
Oh, yeah, let me,
Good.
so I can go back.
Affinity was-
Yeah, affinity is I like STEM, and efficacy is I'm good at STEM.
Does anybody else have one more question? Sean?
How much of this is reusable? How far is that reusable between rockets, or is that one time?
Oh yeah, so everything in the rocket is reusable except the engine itself, and the engines go for, they're between $1 and $2 a piece, depending on how big they are. But yeah, everything else you can use over and over again.
All right, thank you very much. Let's move on to our next